For my curve analysis, I chose the fourth function, which is x squared minus 4x over x plus 4 squared. The first thing we do is make a few predictions. I noticed here that there will be a restriction that x cannot equal negative 4 because the denominator has a double factor of x plus 4. Factoring the numerator confirms that this will in fact be an asymptote. The horizontal asymptote, meanwhile, will probably be at y equals 1 because the numerator and denominator have the same leading term, which is x squared. We don't yet know enough to say if this asymptote is an actual restriction on range, however. We can also say that the x-intercepts fall at the points 0, 0, and 4, 0 because the factors of the numerator are x and x minus 4. Without doing any complicated calculations then, we get a pretty good idea for a few important features: domain, asymptotes, and x-intercepts. Now for the complicated calculations. We need to find both the first and second derivative. The first derivative will give us information about turning points and some inflection points, as well as direction. The second derivative will give us information about inflection points and shape, or concavity. To find the first derivative, I expanded both the numerator and the denominator, and then used the quotient rule. The quotient rule states that f prime of x is equal to the derivative of the numerator multiplied by the denominator minus the derivative of the denominator multiplied by the numerator, all over the denominator squared. So the derivative of the numerator is 2x minus 4, and the derivative of the denominator is 2x plus 8. I get those values from the power rule, which I won't go over. Anyway, the numbers look like this. Then I expand both terms in the numerator so that I can combine the two parts. And that looks like this. You can see with the numerator of the derivative, I factored out a 4 and then factored what was left. The factored form is more useful for finding the features of the function, so we'll come back to that later. The expanded form is more useful for finding the second derivative. Now, technically I could simplify this further by dividing out an x plus 4 factor from the numerator and the denominator, and in this case that would probably be alright and would make my job far easier. However, when you remove a factor like that, you fundamentally change the function. If there weren't more than one of this factor in the denominator, removing that factor would remove an entire restriction, and while it doesn't remove the restriction here because we have 4 of these factors, I can't assume it doesn't change the function or change the result I'd get in the second derivative. So I've elected not to simplify this function before finding the second derivative. Now, to find the second derivative, I repeat what I did to find the first derivative using the quotient rule on the first derivative, except for I used the chain rule to find the derivative of x plus 4 to the power of 4. It ends up looking like this. It gets very long and very complicated. I split it up into sections, and I checked my work frequently to make sure I was staying on track. It comes out looking like this for the second derivative. Now, a part of me expected the factoring of the numerator of the second derivative to be much more difficult than it actually was, but I had a little hunch when I looked at it, and sure enough, the fifth root of the constant after factoring out a negative 24 is 4. Now, this is a fifth degree function, which means that meant there could be 5 factors which all had 4 as the constant term within the factor. I thought that was too perfect to not be the case, and knowing the constant was negative, there would have to be an odd number of factors with a negative constant in them. So I started with 4 of them being x plus 4 and only 1 being x minus 4, and that turned out to be the case. At this point, I divided out the 4 x plus 4 factors from the numerator, leaving x plus 4 to the 4 as the denominator. Anyways, from here, the calculations themselves aren't as difficult to keep track of. So, using the first derivative, we can find vertices and intervals of direction. The x value of the x-intercept on the first derivative is also the x value of the turning point on the original function. Therefore, this function has one vertex where x equals 4 over 3. We substitute 4 over 3 for x in the original function and find that f of 4 over 3 equals negative 1 over 8. Therefore, the vertex is at the point 4 over 3, negative 1 over 8. So, with 2 x-intercepts, one at the origin and one at 4, 0, and a turning point at 4 over 3, negative 1 over 8, the only thing I needed to start graphing this function was a couple of bits of information about direction. So the limit as x approaches infinity in the positive direction is 1 from the bottom, and the limit as x approaches infinity in the negative direction is also 1, but from the top. At this point, I started sketching a graph, and I found that with only one turning point, there's only one way this function can behave, and that's not with infinite range. The vertex must also be the absolute minimum point for f of x. And I did some simple substitutions to test this, and it works. So f of x is increasing when x is less than -4, and also when x is greater than 4/3. F of x is decreasing when x is between -4 and 4/3. Now for the second derivative, which gives information about inflection points and concavity. The x-intercept of the second derivative will give the x-value of inflection points on the function. There's only one x-intercept on f2' of x, which is at 4, 0. We already know this as the x-intercept of f of x, which saves a calculation. 4, 0 is both the x-intercept and the inflection point on f of x. Therefore, f of x is concave up when x is less than 4, and concave down when x is greater than 4. This gives us all the features of the function and completes the curve analysis. I've drawn f of x in red, f' of x in blue, and f2' of x in green. Anything that's colored is coded to whichever function or derivative it was drawn from. I hope this video is what you were looking for, and that it explains everything thoroughly and clearly. Goodbye!